Good morning.
So today we'll continue with what we were doing last time, that is looking at the boundary conditions. And I recall we dealt with the electric wall, and now today we just want to show you a dual to that electric wall. And this is what we call the magnetic wall. Like I said before, a magnetic wall does not exist in the physical sense, but it's a mathematical abstraction that is usually useful when you're trying to solve field problems using computer applications, so to speak. So what we can say is that with the magnetic wall, all we require is that the tangential component of the magnetic field intensity becomes zero at the boundary, that it vanishes. Now the conductor is then described as a perfect magnetic conductor, or a PMC. And when you start using computer application packages such as Microsoft Office or Agilent ADS, or Advanced Design System, or even the High Frequency Structure Simulator HFSS, you'll get such kind of definitions of PMC and PECs. So it shouldn't be such a mystery. So we call it a magnetic wall, and like I said, it doesn't exist in the physical sense, but we can always approximate it with a corrugated surface. Okay, say for example, anyone has seen those coils we use for putting up curtains, you know, the springy things. If you had one wire that is made in that form, and we say that it's varnished, that it's insulated, the coils are insulated, then we can see that there will be no axial current flowing through the wire, but the current will be flowing almost circularly, especially when the coil pitch is very, very tight. And therefore, in such a case, the tangential electric field along the wire will be, or magnetic field will be zero, because there's no axial current flowing. Okay. Now the magnetic one is just useful for the analysis in some electrodynamic field problems, especially things like planar transmission lines, such as what we call the microstrip lines. Microstrip lines are they are just like the PCB tracks that you are already conversant with, only that when you're making a PCB for low frequency, you usually also etch out the ground. If you are using a double-sided PCB, you'll etch out one of the conductors or the conductor plates at the bottom. But with the microstrip, what happens is that ground plane is that one side of the PCB is not etched, and you etch your signal lines on one side of it, on the other side of the PCB, and therefore the currents will be, or the components will be connected between the top side of the PCB and the bottom side. The bottom side that is intact is usually called a ground plane, and therefore that kind of circuit will be called a transmission or a microstrip line kind of circuit. This is usually very useful for very high frequency applications. So when we put that the tangential component of the magnetic field is equal to zero at some of the interfaces, the problem is simplified because it then has the current and voltage characteristics of a transmission line that is terminated in an open circuit. So for the magnetic wall, therefore, we have the following conditions. That one, for the normal components of the fields, is that the normal component of the electric displacement is equal to zero, it vanishes. And as well, the normal component of the magnetic field intensity or magnetic field flux density also vanishes. Who can say why this one vanishes all the time? Can we have someone hazard a guess early in the morning? We have seen even for the electric wall, that B was also equal to 0. Any guesses? I know it's early, but any guesses? Well, what you can do is just recall where these equations come from. These equations come from the Gauss law, that is the divergence of the fields themselves. And we say that the divergence of B, because B is a solenoid vector field, then the divergence of B is going to be equal to 0 all the time anyway. So the tangential components of the fields are such that the tangential component of the electric field is going to be discontinuous at the surface, and it will be equal to the minus of a magnetic current density, which we shall call Ms. Although we are calling it a current, remember M of S will be measured in terms of volts per meter. Okay, it's in volts per meter. And the tangential component of H is going to vanish, as we have seen already. Now, because B is a solenoid field, we can define, now we'll look at what we call the potential theory. And the potential theory is important to us because if you look at the Helmholtz equation that we dealt with, it's the equations for E and H are actually vector equations, and therefore we'll have to be solving 3 components all the time for 3-dimensional vector fields, so to speak. So it's usually important, nice and convenient if we could use a formulation that just requires only one type of function, so that we just solve one and derive the others from the rest. And therefore, we start straight away from the magnetic field flux density, and we call this the potential theory. So since the magnetic flux density was seen to be a solenoidal field, then it can always be defined as the curl of a vector potential field A, such that B is equal to the curl of A. Okay? Now, for fields with a harmonic time dependence of the form exponent of j omega t, then the curl of E will be given by the minus of j omega b, and we see that that is going to be the minus of j multiplied by the curl of E. And since we have curl here and the curl the other side, we can always combine them together, and we see that the curl of E plus the j omega A, or the time derivative of A, must be equal to 0. And immediately we have seen this, that the curl of E, or of the curl of this total vector, is equal to 0. We immediately see that this vector must be an irrotational vector, and therefore we can define it as as the gradient of a scalar potential, so to speak. So thus E is seen to be lamellar or conservative or divergent, curl-free, and therefore we can express it as the gradient of a potential function, which we shall call phi, such that the E plus the time derivative of A is equal to the minus of the gradient of phi. Remember, this negative sign that we use here in the definition is by convention, because when we measure things in the lab, they are always pointing in the right direction. And therefore, we can therefore write E is equal to the minus gradient of phi minus the time derivative of A. If the medium has mu, epsilon, and sigma that are scalar constants, that is, we are saying that the medium is simple, it's homogeneous, isotropic, and linear, then we can always write that the curl of H is going to be given by 1 by mu times the curl of B, so to speak. We are dividing it. We saw that B was equal to mu multiplied by H, and mu being a scalar, then it doesn't have a spatial derivative. Therefore, we can take it out, and we just are left with that value there. And we say that this is the Ampere circuit or law, and that we connect it to the displacement current density plus the conduction current density. And therefore, when we expand the divergence or the curl of A, we get that the gradient of the divergence of A minus the Laplacian of A is equal to the minus of j omega mu epsilon multiplied by the gradient of phi plus j omega A plus multiplied by mu of the conduction current. Now, what you are going to do is to try and remove this expression here from that, from this value here. And what we are going to say is that we are going to let one of these values, that is the gradient of phi, is the only one remaining here, and therefore we'll define it in terms of A. So when we open the brackets all through, we see that here we have a minus omega squared mu epsilon multiplied by A. And remember, we called mu omega squared multiplied by mu epsilon, we called it k squared. And where the k squared, we call it the wave number. And therefore, we can always take that value to the other side, and we have that the gradient of the divergence of A minus Laplacian of A minus the k squared of multiplied by A is equal to the minus of j omega mu epsilon gradient of phi plus mu multiplied by j. So all we need to do is to try and eliminate the gradient of phi by invoking certain conditions on what this gradient is going to be. We are going to say that this gradient and that gradient must be the same. That is, the gradient of the divergence of A must be equal to the minus j omega mu epsilon times the gradient of phi. So this is what we are going to do in the next. This, once we set it up as that, we call it the Lorentz condition. It's different from what the Coulomb's condition that we had before for static fields. The Coulomb condition just set the divergence of A is equal to 0. But if we did that, then for dynamic fields, we will see that the equations become inconsistent. And therefore, this correction by Lorentz came and helped there to reduce the equation into the Laplacian of A plus k squared A equal to minus j omega mu multiplied by j. And this equation, therefore, is called an inhomogeneous Helmholtz equation for the vector potential for the vector potential field A. From Gauss' law, we have that the divergence of E is equal to the divergence of our definition, and we get it is equal to rho, or the volume charge density, free charge density, divided by epsilon. Or in other words, when we multiply through, we see that the Laplacian of phi plus j omega multiplied by the divergence of A is equal to minus rho by epsilon. But if you look at this, we can see that the divergence of A is exactly equal to the minus j omega mu epsilon multiplied by phi, where since these gradients can now be dropped. And therefore, we see that we now have a potential or a Helmholtz equation in terms of the scalar electric potential phi there. And this is inhomogeneous as well because of the forcing function that we have in there. So we call this the inhomogeneous Helmholtz equations for A and phi respectively. Now, let's consider a unit current source, that is a current source of strength unity, localized at a point x prime, y prime, and z prime. The primed coordinates are going to be called the source coordinates, and the unprimed coordinates will be the field point or the observation point where we are observing the fields. So in the Cartesian system, we have it as shown there. That is, our origin is at this bottom. Then our current source is at that point. And our field point, which is P, is at that point. And it's R, its position vector from the origin is R. The position vector of the source is R prime. And therefore, the position of P with respect to the source point is just R minus R prime. So this J is a point source, just like what you have in circuit theory, what you call the impulse or the unit impulse function. So this is a current that is localized in space as a point. So we can represent this source in 3 dimensions as follows. That is, we'll have a component in the x direction, which is delta x of minus x prime. That is, this is just going to be 0 if x is not equal to x prime, and it's going to be unity when x is equal to x prime, and so forth for the y and the z direction. And this, we can always reduce it as delta of r minus r prime. This is called the Kronecker delta or the Dirac function, as you have already met them. But this is a special Dirac function rather than the time Dirac functions that you used when you are dealing with Fourier transformations or Fourier transforms. So the Dirac delta function has the following properties, and this is very important to keep in mind because we shall use it in many cases to solve our problems. So it says that whenever R is not R prime, the Dirac function is going to be equal to 0. Now, if we were to integrate over the volume, we integrate the Dirac function over the volume, it's going to be unity whenever R prime, that is the source, is enclosed within the volume in which we are integrating. It is going to be equal to 0 whenever that vector is not part of that volume. And this will help us to exclude singularities in our problems. That is, all we have to do is to define a volume V around the source, and then we integrate our stuff outside that volume. As long as we are outside, we can always remove the source from the equations. If we have an arbitrary vector or a function f that is continuous at the source point, then the integral over the volume of that function multiplied by the delta function is going to be given by the function, the value of the function at the source point whenever the source point is within V. And it's going to be 0 when the source point is outside V. This is what you call in Fourier transform the sifting law. That is, you are sifting out the values. So a current source that is directed along the unit vector R at R prime can be expressed as follows. It's just going to be given by J equal to R cap multiplied by delta of R minus R prime. I'm just leaving out the vector sum here or the vector subtraction here because it doesn't, just for convenience, so to speak, it doesn't change the results. So the vector potential is therefore going to be a solution of the Helmholtz equation given as the Laplacian of A plus K squared A is equal to the minus of mu. Remember that all this is J, it was mu J, and now we are using our J that we have defined here. So what does it say? As long as two vectors are equal, if and only if they are parallel to each other. And therefore we say the following. A must therefore be directed along the direction of R cap. Okay? And therefore we can always write that A is equal to R cap and multiplied by a scalar amplitude A. Therefore, this will allow us to convert the vector Helmholtz equation into a scalar, whatever Helmholtz equation of that nature. And this is where now we start applying the properties of the Kronecker delta or the Dirac delta function that we have just met. So, from the properties of the delta function, we can say that A is going to be a solution of the homogeneous Helmholtz equation whenever this R is not equal to R prime. Okay? That is, as long as we are integrating away from the source point or outside the volume that contains the source, then the equation we have to worry about is an homogeneous Helmholtz equation. By homogeneous, we are saying it's equated to 0. It doesn't have a sourcing function. This is the same way you solve mathematical problems where you had forcing functions and you looked for the characteristic equation. And this is like a characteristic equation for this particular kind of system. So we'll assume spherical coordinate system that it will be centered at the source point. Okay, and note that A must therefore have a spherical symmetry about R because the source term itself does not contain any angular variations. You can see that the source term itself has only R minus R prime. It's only a function of the distance R from the observation point from the source. It doesn't contain any angles in it. So in the spherical system, we can see that if the A should be the same in all directions around the source point, so to speak. And therefore A must be a function of the radial variable, which we shall now define as big R equal to the modulus of, or the length of the vector connecting the source, the field point to the source. And therefore, the solution of the homogeneous Helmholtz equation, we'll have to have it to put the value of the Laplacian in the spherical coordinate system and add the following. Okay? Or once we open up the brackets, we'll get d2a of dr squared plus 2 by r dA dr plus k squared A is equal to 0. So this is the homogeneous Helmholtz equation for A in the spherical coordinate system. For the spherical coordinate system, I'll ask you to look at the class notes after this lecture, or you can look at a mathematical book or an electrodynamic book. We don't want to go into the spherical and so forth. I think in the class notes, I've also given that kind of derivation. So, just like we did in mathematics, we can always take or make educated guesses as to the form of the solution. So we are going to say that let the solution of A at R be given by a function f of R multiplied by the exponent of minus j k multiplied by R. So all we need is that fr be analytic at R so that it has a derivative at that point. So using this in the differential equation, what we get is that we'll get this following form. And now I can give you maybe 1 minute or 2 minutes to try and see that this is actually the case. So use this expression, okay? Sorry, what did I do? Use that expression in the following. Scheiße. 70. So you use that expression that we have there in this equation, in that equation here. This equation I'm talking about, that equation, okay, this equation, and see that the value that you get is that value there. So just take 2 minutes and try to practice to do a bit of differentiation. So are we happy with the value? Well, I don't know how we are going to go through this this course if we are going to be silent to each other.
Could you show the other equation slightly?
Which one? The derivative.
Yes, the original derivative that we had to apply.
This is the derivative we are using. This is the Helmholtz equation that you are dealing with. It came from that. So all you are supposed to do is to put the expression or the guess that we have for the solution. We put it in this value, in this equation, and prove that for that, this is going to be equal to 0. Once you prove that, then it means that the solution that you have guessed is a solution. It doesn't mean it's the solution, but it's a solution. It's a valid solution.
Excuse me, sir.
Yeah.
In the next page,
Yeah.
No, this page actually.
Yeah.
Why aren't we putting in the whole expression of A? It's written F into R exponential minus JKR. Why are we just putting in F? The solution just reads.
Because this one, because this one, what happens is that this one will always be its own derivative, isn't it?
Yes.
Everywhere we have A, it will always have an exponent of minus JKR. Whatever you do, it will multiply everywhere, isn't it? And therefore, since we can bracket it out, and it can never be equal to 0, then it's only this which can be equal to 0. Do you get it?
So it has to be ignored.
Which one? No, you're not ignoring it. You are not ignoring it. This is what you are dealing with. You are taking the value of A as it is in here. Agreed? So you'll put in also the exponent FR multiplied by the exponent of minus JKR, all right? For the value of A. Agreed?
Yes.
So you will do the second derivative, then you'll do the first derivative, and then you'll multiply it by the whole A. And you'll see that there will be a D2R, a D2F by D2R multiplied by the exponent of minus JKR. Agreed?
Yes.
Correct or not correct?
Yes.
You are going to introduce that thing you call the product rule and the likes. So in the end, what will happen is that in this particular expression here, the derivatives of exponent of minus JKR are these ones. You can see some minus 2 J2K.
Yes.
You can see another J2K squared and so forth. All these K's came from that. You get it?
Yes.
But since this one, once you differentiate exponent of minus JKR, you get minus JK multiplied by the exponent of minus JKR. Agree?
Yes.
So this will appear everywhere we are differentiating A. And therefore it can be left out because the exponent of minus JKR is not equal to 0 anytime. Except at R equal to infinity. All right?
Yes.
So in the end, you are just left only with the derivatives of f of R. So this equation just becomes that kind of value. And what we want to do is to try and see what f of R is going to be, or what value of f we can get out there. So we have simplified our equation from a differential equation in R to a differential equation to a function of f of R. And this is now what we are going to try to find out, what value or what expression of f, or how does what would be the form of f that will make this equation go to 0 as that is requiring it to be. And this is what we are calling the guess again. We'll put another form for it, and we'll guess it as follows. That is, we define f of R as a potential function of the form fr equal to a constant divided by R. If such kind of functions are called potential functions because if you look at the gravitational field, the gravitational field itself, gravitational potential, is usually a constant g multiplied by the masses of the two objects and divided by the square of the radius, or of the distance, so to speak. And if we integrate that, you just get that constant multiplied by or divided by that value. This constant, we are going to define what is going to be in the end. But for now, this is the value that we want. Now, take this value that we have here and put it in here. Do the differentiations now for this kind of value and add it here. Then see what kind of equation you get. See whether you get 0 on both sides. I'm assuming you already proved for yourself that this is the case. Now just put this, now use this solution for f of r in this differential equation and prove for yourself that this function, if f of r was defined as shown, then it will be a solution of this problem here.
The uppercase R and the uppercase K and lowercase k are the same, or?
No, the lowercase k is what we call the wave number, my friend.
Oh.
Isn't it? The big K, I'm calling it a constant. The small k is that a propagation constant for the wave. They are not the same.
Okay.
Yeah. So did we prove it?
There are two terms that are not cancelling. There is the term with J2K and the term with J2K squared.
Why wouldn't it do it?
The power,
so the first one is what?
the power of the K. Or the first term is 2K divided by R cubed, and then minus 2k divided by r cubed plus 2 small k capital K divided by r squared minus j2k squared k over r squared.
Let me check for you whether I've left out something. We potential functions. And the differential equation, did you get it the way it's written there?
I had not completed proving. Let me go back to it.
Yeah, because there may be a problem in the way I've written the differential equation in terms of f. So it's important that we make sure that we have a correct equation there. Success equations. Success equations. The equation is right. So that one is 2k by r cubed plus 2 multiplied by r minus j 2k into the minus of k by r minus j 2k squared by r multiplied by k squared multiplied by k. So we get 2k by r cubed plus minus 2k, and it's r squared by r cubed, so that one cancels, and j2k multiplied by r squared minus, so I think the problem should be k squared. Yeah, the problem is actually the last term in the expression for this expression. There is a square which I've put here, which is wrong. Okay.
Or then in that case, it does lead to 0.
This is wrong. This is not correct. So remember to solve to copy to whatever to correct that one. Okay. df squared r dr squared plus j2k squared. Remove the k squared. So once you have that, of course, then things are okay. We can continue. And therefore, we can see that since that we have proved for ourselves that f of r is k by big R, then we can just simply write our solution as a of r is equal to k by r and multiplied by the exponent of minus j k r. Remember, like we said, this is only a possible solution. We can only show that it's a solution if it gives us the correct values that we need. So now we try to determine what k is going to be. What we are going to do is to integrate a of r throughout a spherical volume of a small radius that is centered at the source. That is just like, I don't know whether you have dealt with residues, complex number for whatever function, whatever integrations. For that one you meet in 5th year, I think. So what we can do is to, when you have a discontinuity, we can see that AR is not going to be defined when R is equal to 0. It will go to infinity. So what we are going to do is to try and remove that infinity point, which is at at r equal to 0, and r equal to 0 is saying that the field point is exactly at the source point. So we are going to remove that source point by defining a small volume, spherical volume about the source, okay, centered at the source with a radius r0, and we require that r0 is equal to, is a very small value, and we'll take the limit as we shrink our volume smaller and smaller and collapse it to the source point. Okay? So we are going to use the shifting property of the delta function to determine what k is going to be. This is what we are going to do. We start with the Helmholtz equation and integrate over the volume, and we see that that is going to be given by the minus of mu multiplied by the source term. And since this value, the integral of the Kronecker or the Dirac delta over the entire volume is equal to unity, and we can see that this side just becomes the minus of mu. So the only thing we have to worry about is this other side. Now, if we were to try to take the radius of the volume towards 0, then the k squared multiplied by a must go to 0 as well. Okay? Because we are making it smaller and smaller, so to speak. And therefore, in the end, we are going to be left only with the Laplacian of a alone, which we can always write the Laplacian as the del dot del of a dv, or the divergence of the gradient of a dv equal to 0. And once we see this kind of value here, then it means we can always apply the divergence theorem to convert this volume integral into a closed surface integral. So this is what we do in the following. That is, we make this, use the divergence theorem and define and change it into the surface integral, closed surface integral of the gradient of A over the surface of the sphere S. And we say that that is going to be equal to the minus of mu. And we say that the S would be the surface of the volume of integration, whose radius is, of course, R0. Now, the element of area can be expressed as follows. If d omega is the angle, okay, or the solid angle subtended by a surface ds on a sphere of radius r0, okay, at the center of that sphere, then ds will be given as the normal vector on that surface multiplied by the radius squared and multiplied by the solid angle d omega. So n is the outward unit normal because the divergence theorem requires an outward unit normal on S, and d omega is the element of solid angle subtended by ds at r prime. A solid angle, the way we can understand it, I always give this analogy of an ice cone. The angle of a cone of ice. How do you explain it? Okay, we are conversant with the two-dimensional kind of planes and triangles and the like, so we know what that angle is going to be. So for a cone, the angle is round, and then it's just going to an apex. So that is usually referred to as a solid angle, and it will be measured not in radians, but things we call steradians. This we shall see later as we define it more correctly. And therefore, we can always integrate our surface integral as the gradient of a dot n cap d omega is equal to mu. Now, since A is only a function of r alone, then the gradient does not include the derivatives with respect to angle. That is theta, the elevation theta, angle theta, and the azimuthal angle phi on the spherical coordinate system. And therefore, we are only interested in the r direction, okay? And therefore, we see that the gradient of A will just simply be the dA and divided by dr. And this we therefore place into our equation, and we see that this value here, since the omega does not matter, we just put it that the normal value or the full sphere will have 4 pi steradians, and therefore just multiply that by 4 pi steradians, dA dr is equal to the minus of mu. That's all you need. So when we evaluate the derivative of A at r equal to r naught, and take the limit as r naught is allowed to shrink to 0, then we see that this value is going to be given by the 4 pi r naught squared of k, and remember what the value of A is, so we differentiate that one with respect to the r, and we get the following equation. And in the end, you see that this value, as r goes to 0, okay, this becomes unity, and we are left with just these values here. That the minus of 4 pi k is equal to minus mu, or rather, k is just simply mu divided by 4 pi. So that's what the potential theory means, and therefore our A becomes the following form. That A is equal to the r cap multiplied by mu over 4 pi multiplied by big R, because we saw that the k is just mu by 4 pi, so it's just going to be 1 over big R with this definition, the exponent of minus jk, and the modulus of r minus r prime. Remember, this modulus here is the definition for r. So A is therefore seen to be the solution. Since we started with a unit point source, then A is the solution of a point source, and it's usually called a Green's function, and denoted as g of r given r prime, or the value in the Cartesian coordinate system, or simply that equation there. Okay, Green's functions are functions that you are going to get many times, especially when you are dealing with point sources, and even in mathematics you meet it quite a lot. So in general, since any general current distribution J can be expressed as a superposition of weighted point sources, just like you did the Fourier series expansion of complex signals, we can always write J as a superposition of weighted point sources. By weighting, we are saying that we'll have different amplitudes, and when we add them together, they all make up J. And therefore, A will be given as mu by 4 pi, the integral over the volume of the source current density divided by the radius vector between the observation and the source, and multiplied by that expression there, exponent of minus jk r minus r prime dv. And this, in terms of the Green's function, is reduced to that value there. So, because of that, we have what we call retarded potentials. This means that, say for example, in our situation here, say on Earth, the sun releases a photon of light, and that photon of light arrives at the Earth's surface 8.33 minutes later, okay, depending on where the sun is. So the same kind of thing, we say that that light does not arrive here instantaneously, but it's delayed. We are always basking in a phonon or a photon of infrared light from the sun that was done 8 minutes ago. Okay, so if the sun goes off now, we'll only get to know that it has gone off 8 minutes later, so to speak. So the static vector and scalar potentials are solutions of the inhomogeneous Helmholtz equations of that form. This is because the k only appears, the k squared we saw only appears when the the fields are varying with time, and also sinusoidal. They are varying in time sinusoidally, so to speak. That's why we had that k squared. But now the k squared is going to be removed because we don't have time derivatives. The time derivatives are all equal to 0, and therefore the Laplacian of A is just equal to the minus of mu j, and the Laplacian of phi is equal to the minus of rho by epsilon. This is something you must have met in third year. Now, what we are going to say is that even for the dynamic case, okay, we see that the solutions in the scalar case is that. So even for the dynamic case, then we can only just add in a time dependence into the fields and assume that they are going to have the same form of solution, so to speak. But not on the other side what we have. We are saying the vector A at a time t is going to be produced, to be the A produced by what the current was at a time t minus r over Vp. Vp is a vector, is a velocity, and therefore this is the distance of the source point from the field point from the source, and therefore it would take that distance divided by the speed of the propagation of that effect to come to us. Okay, so say for example, for the light coming from the sun, we can say that it would be now replacing this by 8.33 minutes, so to speak. So this is then integrated over volume. So the only thing we have done in these expressions for the field, the static fields, is to add the element of time variation, and we know that, and we note that it will take time for the effect for the perturbation at the source to arrive at this source point, and the same for the other type as well, where we are using the volume, the free charge density, or at a time t earlier, that is r by Vp time earlier. So Vp is of course going to be given by the square root of 1 by mu epsilon, which is the speed, the phase velocity of the electromagnetic field. R is of course given by that in Cartesian coordinate system, and is the distance of the field point from the source. So the term T minus R by Vp will emphasize that the values of the volume charge density and the conduction current density at T less, okay, T minus R over Vp will be the values required to compute phi and A at R, at, and T. And that is each element of a charge rho multiplied by dV, or current J multiplied by dV, okay, that is an element of current or an element of charge contributing to phi or A at R and T, has the same form as the static case, taking into account the propagation time from the source to the field point. This is what is causing all our problems when we are now dealing with electrodynamic fields, the retardation of the effects. And it brings in a lot of other things that we shall see later. So because of the retardation effect, A and phi in the dynamic case are called retarded potentials. Now, let's consider a current element that is in the form of a straight conductor of length L, much less than or much shorter than the wavelength of the electromagnetic wave that we are trying to deal with. And remember, the wavelength is the distance between two adjacent crests on a sinusoidal wave in space. And we let that the strength of that current be Liz, that is, it's oriented along the z direction and located at the center or the origin of the Cartesian coordinate system as we have shown here. So this is our current element. Just, it could be, since current only flows round a circuit, so this you'll have to look at as an oscillatory current that is going and terminating there and coming back down and so forth. So it's just sinusoidally varying along that element there. So the origin is at that point, and then we are going to take our field point P so far away from the from the current element, such that all these three vectors, that is the vector position vector r of the source point of the field point, and the two vectors from the ends of the current element, become essentially parallel as far as we are concerned. They all seem to be coming from the same point, so to speak, by the distance that we are dealing with. So differences in the distance to the field point at x, y, and z from the different points or current on the current element. Okay, this should be on the current element on the wire of a given radius will be essentially unimportant. That is, r prime, r, and r double prime are going to be essentially the same when you are looking at the magnitudes. That is, the differences are of no consequence. But we have seen that those differences are also will also appear in the phase factor, which we call the exponent of minus jk multiplied by r. Okay, so that is where we are going to take the differences as important, because k can be a big value and therefore the phase can be very large as well. So we assume a uniform current distribution on the wire. That is, the current is Iz is a constant. Okay, and the integral of the current density over the wire cross section then yields the total current Iz flowing through it. We are saying that the current is just Jz. That is, in the solution for A, we are using current density. But if we integrate over the cross section of the wire, then we'll get the total current Iz flowing. It will be a double integral, so to speak. So for a filamentary current, filamentary means it's a wire of infinitesimally small cross section. Okay, it has almost 0 radius. So we can therefore write that A is going to be given by mu by 4 pi Iz at a time t minus r over dp divided by r dr. So since the current is only in the z direction due to the infinitesimally small cross section of the wire, then A must also be entirely in the z direction as well. That is, the A at the field point is also going to be in this parallel to the current. So the integral can be accomplished by simply multiplying the current by the length of the current element, L, as long as L is much shorter than the wavelength. And then we can see that Iz is essentially uniform over the length, and we can write A as just mu multiplied by L over 4 pi multiplied by R Iz of that the current or the time dependence of the Iz. Remember, the spatial dependence of Iz is equal to 0, so Iz is constant, but it's varying with time. So if the fields have a harmonic time dependence of the form exponent of j omega t, then you can write that B is the curl of A, E is given by that expression that we got before. And we know that A is given by those values that we have already seen before. And this equation here now, exponent of minus jkr, now takes care of that t minus r over vp that we are dealing with. So the retardation of the fields is now contained in the propagation factor, exponent of minus jkr. And r is, of course, expressed as shown there. So A and phi are then related through the Lorentz condition, that the divergence of A is equal to the minus time derivative of mu epsilon multiplied by phi. And The propagation constant is given by K equal to twice pi by lambda, or it's just omega by C given as omega multiplied by root mu epsilon. The retardation effect is of course accounted for by the first term, which we are calling here the exponent of minus jk and r multiplied by r. And this amounts to shifting the phase of each contribution to the potential at the field point from each element of current by an amount proportional to r. Okay, and its distance to the, where r is its distance to the field point. So for the steady state sinusoidal potentials, phi will be uniquely determined from the Lorentz condition once we know A, okay? And this will be obtained as follows, that the minus gradient of phi minus j omega A prime is equal to minus j omega by k. We replace the gradient of phi. We know that phi is going to be equal to the divergence of A, and we put it there from the Lorentz condition, and we can see that this is going to be the minus of j omega A. Or in other words, E can be obtained from the magnetic vector potential. Therefore, it tells us we really don't need to know what phi is. Once we know A, we can get what the E field is going to be. If we know phi, we can get what the others are going to be. So we can use either of the potentials, phi or A, to obtain the values of E and H. So A is of course given by that expression that we already met before. And we therefore only need to specify the current distribution, okay? A can be obtained from the current distribution on the source or at the source, okay? And we specify the current distribution in that volume that we are dealing with, and we determine what the value of A is going to be. Once we have the value of A, we can also get now the H field, okay, by taking the curl of A and dividing it by the permeability. And from H, we can always get E by getting the curl of H. And from the continuity equation, we see the following, that the divergence of J is equal to the time derivative of the volume charge density rho. This is something we saw before when we were talking about continuity equation. And therefore, all we need to do is to know what the charge is or what the current density is, and everything is determined. So the volume charge density will be determined uniquely once we have established what J is, okay, and everything is over. So to get the fields, all we need to do is to, first of all, like say for example, you are dealing with an antenna problem, say a Safaricom kind of mast. All we have to do is to know what the distribution of the current is on that antenna. Then we can develop, or we can derive what the vector potential is going to be by integrating that current distribution over volume defined around the antenna. Then we use the curl of A to define what H is going to be, and we use Ampere circuit or law to get the E, and everything will be determined. Usually you will find that the current distribution doesn't even need to be known exactly. We can always get a solution, a fair amount of the solution, by guessing a value for J, so to speak. So any question then? Do you have any question? So we can take a 5-minute break. Okay, we'll meet at 10:14. Then we can continue. I'm going to display the next topic that we shall be looking at now.
Sasa inabaki
kubadilisha lens different.
So we look at what we call the uniform plane waves. By uniform plane waves, we are saying they are the constant phase points or phase points on the wave all appear in the same, in a planar way, a plane, and the amplitude of the wave is going to be the same. It's not that, it does not change. So immediately the amplitude of the wave changes as it propagates. It's no longer a uniform plane wave, but it will be non-uniform. So these plane waves will be solutions of the Helmholtz equation. And therefore now what we are going to propose is to try and get a solution of the Helmholtz equation using the separation of variables method, just like we used when we were dealing with the solution of Schrodinger's equation in physical electronics. So we assume a Cartesian coordinate system. Since the waves are planar anyway, the phase points are planar, they won't be changing in direction, and therefore we can always use the Cartesian coordinate system to simplify our solutions. So in the Cartesian coordinate system, we expand the Laplacian in the form that is the del dot del is going to be given by the partial derivative, the second partial derivative in the x direction, in the y direction, and in the z direction. So a wave equation, or the wave equation for E in a lossless unbounded medium, that is if the medium has sigma equal to 0, okay, that it has no conductivity in it, the conductivity is 0, then we can always write for the E that the place here now, E plus K squared E is equal to 0. Remember, this is what we were using the triangle squared. Remember, this is just a shorthand, but when we are solving problems, we have to replace this del operator by its actual definition. And therefore, we'll see that all we are saying is that the derivative, the second derivative in the x direction plus the second derivative in the y direction and the third derivative, the z derivative in the z direction is equal plus that k squared multiplied by the function is equal to 0. These are the kind of things we were calling the eigenvalue problems, if you recall. It's going to be equal to 0 because what we have said is that there are no sources in the region of space that we are trying to measure E. Rho is equal to 0, and therefore there are no sources. K squared is given by omega squared multiplied by mu epsilon. And immediately you see this formulation where all we are saying is that E is sinusoidal, or it has a harmonic time dependence. So the vector equation must hold separately for each component of E. That is, E itself has an x cap EX plus y cap EY plus z cap EZ. So each one of them has 3 components, this vector here. And therefore we have 3 equations for X, 3 equations for Y, and 3 equations for the Z direction. And all this must hold separately for each component of the vector E. Now, what we are going to do is that we assume that we can always express the X component, or the components of E can be expressed as a product of 3 functions of a single variable each. That is, we'll have that EX can be expressed as an X function, a Y function, and a Z function. And we require that since E is not equal to 0, we require that that product is not equal to 0. And that is the same as requiring neither of these X, Y, and Z to be 0. They cannot be 0. And therefore, when we use that formulation, the Helmholtz equation becomes a total derivative rather than a partial derivative, because each element or each component is actually a single variable derivative. And therefore, we get yz d2 dx squared of x plus xz d2 dy squared of big Y. The big Y is missing here, and plus the xy d2 dz2 of z is equal to k squared x, y, and z. Here, you will replace that by the big Y, which is missing in this particular formulation. Now, since we have already required that the product not be 0, then we can divide through by this product here, and we get a value of 1 by x d2 dx squared multiplied by x plus 1 over y d2 dy squared of y, and 1 over z d2 dz squared of big Z, plus kx squared plus ky squared plus kz squared is equal to 0, where the kx squared plus ky squared plus kz squared, we require it to be equal to the original k there. So the kx, ky, and kz are called separation constants. Now, when we look at this equation here, this term is only a function of x, that term is a function of y, that term is a function of the z coordinate. And therefore, it means for this to hold for all x, y, and z, then each of them must be equal to a constant, and that constant must be the same, so to speak. So, you can therefore write it as follows. that x can therefore have a possible solution of the form an amplitude ex of 0 exponent of minus j kx of x plus ky of y plus kz of z. Okay, so try this solution in this equation here and see what you get. That is, we are going to use it, not this equation, but this equation here. Where are you? You put it in this equation, replace this value here, not by the vector, just put the x component of E. Okay? And use that expression for the E that we are dealing with. You get the task? Is the exercise clear, please?
Yes, it is.
Yeah, so try to show that that expression actually holds. Okay, that this expression here holds for that particular equation for the component of x at least. So I guess you have already proved for yourself.
Yes.
Yeah, so we do the following. So we can say that the x component, okay, of the electric field intensity of the wave will be propagating in the direction given by the k vector, wave vector k, which is defined as x cap k of x plus y cap k of y plus z cap k of z. And we can always reduce it as a vector, a unit vector n multiplying the modulus of k, where n cap is just the vector k divided by the modulus of k, which we are calling k equal to that modulus. And this is omega root epsilon mu or mu epsilon, and is called the wave number of the wave itself. Now, since when we don't have any sources or any free charges in space, then the divergence of E is going to be identically equal to 0, and therefore, in the values of E, only two components can be arbitrary. The third one must be linearly related to them. So, since that must vanish everywhere in free space, then all the components of E, that is Ex, Ey, and Ez, must have the same spatial variation. And we have seen that the spatial variation for a uniform field is just that exponent of minus jk multiplied by the distance. So let R, given the position vector of the field point, or where we are observing the wave, be given as R, given by x cap multiplied by xy cap by y, and z cap by z. Okay, is the position vector of the observation of field point from the origin of the coordinate system. And therefore, E of x is going to be given by that value, where we are using the k that we have defined. We shall see that it will be given by k dot r. And remember, the k is just n cap multiplied by k, the modulus of k, and you'll get that r multiplied by that. And since all of them have the x's, we'll separate them as x. Yeah, kx of x, ky of y, and kz of z, and so forth. And Ey has the same spatial variation as before, as the other one. It's constant in the y direction, but with a spatial variation as in the Ex, and Ez the same as well. And therefore, we can express E as an amplitude vector E naught multiplying the spatial variation, okay, in that form. So exponent of minus jk prime dot r prime is called the propagation factor of the wave. And E naught is called the amplitude vector of the electric field intensity. And we note that the E naught is just simply x, okay, the x component, the y component, plus the z component. And it's constant, it's a constant amplitude vector. So a wave propagating through space with constant amplitude is therefore called a uniform plane wave. Now, using this in the divergence equation, we obtain the following: that the divergence of E is going to be given by the E naught dot the gradient of the exponent of that. Here, we have used a vector identity which says that if you get the derivative or the divergence of a constant multiplying, okay, or a function, a scalar function multiplying a vector field, then it can always be spread through, and we'll get that that is going to be given as the vector dot the gradient of the scalar function plus the scalar function multiplied by the divergence of that vector field. Okay? And therefore, what it means is that since the vector field itself, that is E naught, is actually constant, then its derivative is going to be equal to 0 anyway, and that value now, that component is missing from this kind of, from this expression. And therefore, we see that the gradient of the exponent of minus jk dot r is just simply minus j of k prime dot the E naught exponent of that. And this must be equal to 0. Now, for this to be equal to 0, then it means that k and E naught must be normal to each other. So, at least we can say that E naught, or the amplitude vector for the electric field, will be normal to the direction of propagation indicated by k. The divergence condition will therefore restrict the value of Ex, Ey, and Ez, okay, the values they can take so that E naught will always be everywhere normal to the direction of propagation. Now, if you look at the magnetic field intensity, it's given by the amperes or the Faraday's law of induction. And we saw that it was going to be like the curl of E is equal to the minus time derivative of the magnetic flux density, which is given as mu multiplied by h. And therefore, we can always correct it as the minus of 1 by j omega mu, and then the curl of E. Again, we note that E is equal to a vector multiplied by a scalar function called E exponent of minus j k dot r, and therefore we can use again as a vector identity for that and write it as, all we are going to do is to take this value and interchange them, and therefore we are going to get that it's just the same as E naught, that is the amplitude vector cross the gradient of the scalar function. The negative sign has been removed because of the way that we have interchanged the two vectors. And once we get that, we can always get the values. Okay, we remove the values out, and we see that 1 over mu naught k, this should be left as mu, k cross E naught, exponent of that is equal to the k, the mu, and n cross that value there. Now, n cap is in the direction of k, E is in a direction normal to k, to the vector k, or normal to that value there. And therefore, the cross of it must be a vector that is normal to the plane that will contain both E and N. That is, if we were to form a plane, N and E will be normal to each other, but the vector that is formed by N cross E must be normal to that plane that contains both of them. And therefore, we can say that H is going to be given by that value, where we are using the epsilon by mu and changing it to a value given by eta. Eta will be called the intrinsic wave impedance of the medium through which the wave is moving. It has dimensions of the impedance, that is ohms. So, the physical, and once we have that, we can say that, let me go up a bit. Since this is also normal to E, that is H is normal to E and N, then we see that both H and E are normal to the direction of propagation, and they have what we call when we are talking about these waves, we call it the TEM wave, or the transverse electromagnetic wave. Try to get the value for eta for free space. That is, get the value of the square root of mu naught divided by epsilon naught. Mu naught is equal to 4 pi times 10 raised to minus 7 henries per meter, and mu and epsilon is 8.854 times 10 raised to minus 12 farad per meter. Get the value. What would be the value?
.73.
Yeah, so it's 376. So we usually write it as 377 ohms. Now, another expression you can get for that eta is putting mu naught equal to 4 pi times 10 raised to minus 7 Henry per meter, and epsilon is usually given approximately by 10 raised to minus 9 divided by 36 pi. Farads per meter. If you did the same, you'll see that eta for free space is going to be given by something like 120 pi ohms, so to speak. So you have to convince yourself that Henry's divided by Henry's per meter divided by farads per meter reduced to ohms. Okay, Henry's is the expression for what? Inductance, and farads is the expression for capacitance, and farad is just simply coulombs divided by voltage. Henry's would be what? Webers divided by some current, so it shall be something like volt seconds divided by amps, and you'll see that that is going to go to ohms anyway. That's all I can say about it. So once we have solved the problem, those solutions are called phasor solutions, and I'm sure you have met that in power systems, where you deal with phase and whatever magnitude and phase. So quantities that are expressed in magnitude and phase are called phasor quantities, and the E and H that we have computed are in phasor form. To get the actual physical quantity for E and H, we multiply. Remember, there was an exponent of j omega t that we suppressed when we were writing the Maxwell's equations because they were repeated everywhere. There was no need of putting it there. We can solve the Maxwell's equations, then put the whatever the exponent of j omega t later after we get that to get the values. And therefore, for the E, in terms of time and distance, we'll get the real part of the E that we have obtained in our solution, multiplied by the exponent of j omega t, and we'll get a magnitude or an amplitude vector, multiply the cosine of omega t minus k dot r prime. And this is the equation of a traveling wave. It's changing, and it's traveling in the positive r direction because for this phase term here to remain constant, as time increases, we must increase k as well. Increase the k dot r as well for it to remain always positive, constant, so to speak. And we have assumed that E naught itself does not have a phase angle because we can always define our reference point. Remember, although we are using the real part, it doesn't have to be always the real part. You can use the imaginary part if you like of this expression. And instead of getting it, we'll now get a sine wave instead. Instead of the cosine, we get a sine. But conventionally, and in this particular course, we shall be using the real physical quantities as the real part of that expression, the phasor multiplied by the exponent of j omega t, the real part, rather than the imaginary part. But remember, if you took the imaginary part, nobody is going to penalize you. It's still a solution, so to speak. Now, when we look at that, the expression for E can be expressed as follows. We can always write it as cos omega into t minus k dot r over omega. Okay, it's the same expression, only that now we are removing the omega out, so that is expressing that. And if you look at this, we see that this now is in the form that we saw before of a retarded potential. And therefore, we are saying that E, a dynamic electric field intensity, is a retarded quantity as well. Now, suppose theta is the small angle between K and R. We are saying that R is the position vector of the field point from the origin of the Cartesian field. The wave is propagating in the direction of K. So it doesn't necessarily have to be traveling towards us. It could be going away from us. It could be going in a direction different, okay, at an angle theta to us, and so forth. So if theta is the small angle between r and k, then we can always see that E is going to be given by the omega into T minus K R, that is the modulus of K and the modulus of R, and multiplied by the cosine of the small angle. That's the definition of the dot product of vectors, and divided by the frequency, angular frequency of the wave. And therefore, we can see that this is going to be given by, so if you recall that K was given as omega by C, then this becomes the value omega into T minus R cos theta by C. And we see what we were talking about, dividing by the phase velocity of the electromagnetic wave. So example, if h of r is given as h naught, the exponent of minus jk dot r for a TEM wave, obtain an expression for the E of r in terms of h of r. So we know what the magnetic field intensity is, and all we are trying to seek for is the electric field intensity. So H is given by that. Then we are going to apply Ampere's circuit law. Remember, the medium was lossless, so we can always use everything will be homogeneous kind of thing. So we are going to use that value, okay, that from the circuit law, the Ampere circuit law, to get the value of ER. And we see that this is just going to be given by JK over J omega epsilon and eta cap, n cap cross H. N cap, remember, is the unit vector in the direction of K. And therefore, we see that E is going to be given by the minus of eta, that is the intrinsic wave impedance, multiplied by the cross product between the direction vector and the magnetic field intensity vector. And that brings us to the end of that value there. So any question there? Questions? Then I'll introduce the new topic then. We are continuing with the plane waves. So in the case of the TEM waves, okay, and we are going to look at what they are in lossless media. In the case of TEM waves, we have no axial components, where we are saying that the wave is traveling in the in the z direction, and therefore the E field and the H field components in that direction are equal to 0. That's why we have a completely transverse electromagnetic wave. That is, the fields themselves are mutually orthogonal and orthogonal to the direction of propagation. So the reduced Maxwell's equations therefore have the form that the transverse curl of ET is equal to 0, the transverse curl of the transverse component of H is equal to 0, and the axial components are given as shown there. We are now using gamma, although we are talking about lossless media, this gamma is going to be given a value that is different from a complex value before. This is assuming that we had a general kind of medium. Now, because these transverse components of the fields are rotational in the transverse field plane, then we can express the transverse components as gradients of scalar potentials, which we are calling phi for E and phi m for H of t. And since the divergence of E is equal to 0 because there are no sources or no charges, then E of t will be given as a Laplacian, that is, we'll be solving the potential, the scalar potential for E, which is that Laplacian of phi is equal to 0. The electric field is then given by the gradient of that phi that we have obtained and multiplying it by the minus jk of z. So this is the phasor potential or the phasor electric field intensity. The E of t must also satisfy the complete Helmholtz equation. That is, where del is not just simply in the x, y, and in the x and y direction, but the complete one, including the z. So it must be given by the Laplacian of E of t equal to k squared, E of t equal to 0. So even if we have defined our value as that, it must also satisfy this equation here. This should have been a t there as well. So that del is given as that value, and therefore you can get the value of del squared as del of t squared plus gamma squared. And if we place this down, we get that this expression now comes in, that the transverse component must be equal to plus kc squared, and that is equal to 0, where kc is just gamma squared plus k squared. Or in other words, if we take the gradient, okay, of that equation there, this must be equal to 0. So, in the case of a charge-free region filled with a lossless medium, J is just simply J beta, and it's equal to Jk, and Kc is going to be equal to 0. That is, there will be no cutoff wave number. The wave will travel whether it has 0 frequency or it has infinite frequency. That is, even DC will obey that kind of propagation. So the magnetic field is therefore obtained from that equation there, which we can see is just Z cross E of t over eta. Remember, we said it was n cap, and n cap was in the direction of propagation. And now, since our direction of propagation is in the z direction, we can always replace n cap by the z cap, which is the unit vector in the direction of propagation. And we get that eta is just j omega mu divided by gamma. And this you can always get when we replace gamma by jk. Thus, E is going to be given by the amplitude vector, okay, in the transverse direction, multiplied by the propagation factor, where we are putting minus or plus jkz. Both of them are solutions to the Helmholtz equation, and it's equal to the minus of the transverse gradient of the scalar potential for E, and multiplied by the factor there. We are going now to introduce, we can always introduce, we'll see that when we have positive jkz, it's a wave that will be propagating in the negative z direction, and if we have exponent of minus jkz, it's a wave propagating in the positive direction. This is a different kind of definition as from the physicists. The physicists always use the positive kz as the positive direction, but then the time equation is usually exponent of minus j omega t. So there's no big problem that we have in this particular case. And h is therefore going to be given by that value as well. And we see that those are the equations that we get for this particular equation. Don't get confused by the k naught and k's. These ones I've removed. It's just because I was leaving some of them in when I'm dealing with the lossless. But the k naught is just the same as the general k that I have out here. I will correct this to make them more consistent. So the exponent of minus jkz represents a wave propagating in the positive z direction, because in the retarded form, we will have the cosine of omega t minus kz. And if it's moving in the negative z direction, we'll have omega t plus kz. And therefore, we see that as omega t increases, kz must be decreased for it to keep that argument constant. And therefore, we see that z must therefore be negative for that particular case when you have positive z. So in the expressions, k will be given as omega root mu epsilon, which is omega by c, and eta is omega mu by k, which is just equal to mu by epsilon, which gives us an eta dot of mu naught by that, which is 120 ohms. But if it's a different, a different medium, we'll see that it will be divided. If it's non-magnetic, it will be divided by the square root of the dielectric constant, okay, or the refractive index. If it's both magnetic and whatever dielectric, we multiply it by the square root of mu r by epsilon r for this particular value. So eta is called the wave or intrinsic impedance of the medium through which the wave is propagating. And for the wave propagating in the positive z direction, we can have it that E of x divided by h of y will be equal to the minus of E of y by h of z equal to eta. What we are saying is that if we have a wave with a component Ex, the H field will be in the direction of y when it's propagating in the positive z direction. And we shall see that if we take the direction or the value of eta will be given as follows, or the direction of propagation of a wave will be given as follows. We shall form a vector called E cross H, okay? Once you do E cross H, what you'll get is what we call a power density, and we shall meet that later. Maybe I've already meant it. It's called a Poynting's vector, okay? Once we form the Poynting's vector, it will give us a power density, and the power will be propagating in the direction of the wave. And therefore, for E, x, and Ey, a wave with Ex and Hy, it's x cross y, which is positive z. If in the other case, the field was Ey, and the magnetic field of Ex would get y cross x, and we get that as minus z. But our value is propagating in the z direction, and therefore one of them must change direction. So we can't have Ey and Ex, we must have Ey and maybe minus Hx, or Hx and minus Ey. Not both of them cannot be changed direction. Otherwise, if you change the direction, if you change both of them, the direction will also change. And that's why we have this expression there. So the wave propagating in the negative z direction will be given by Ex Ey h divided by Hy equal to the minus of Ey and Hx, and we see that it will be given a negative impedance, so to speak. The physical fields are then obtained, as we said, is the phasor form multiplied by the exponent of j omega t, and we take the real part. And therefore, this is going to be given by 1, the wave component, which we shall write with a small superscript plus. It will be the wave moving in the forward direction, that is in the positive z direction, plus a component moving in the negative z direction. And that's why we are using a negative value there for it. Okay? So we can see the difference is just omega t minus kz for positive moving. Like we said, that as we increase time, k must be increased to keep this constant. And as we increase time here, this must be decreased to remove the value, and therefore the must be moving in the z direction, in the minus z direction. And h will be similarly given as before, where the h of x of ht of a plus is going to be given by that value, and the other one is going to be given by that value cross that value there to get the value of x. So, example 2. What I can say is that here this should be a negative value because, okay, Because if these are pointing the same direction, this z cross that is going to be a negative value here. Because we saw for that particular case, it is moving in the backward direction and the eta must be negative. So we should have a minus sign, and I'll correct that as we go along. So I'll give an example, then we'll call it a day, because my time is running out. So a uniform plane wave with E in the x direction is propagating in the z direction in a lossless simple medium, and therefore that means it's linear, homogeneous, and isotropic, with a dielectric constant of 4, and a permeability or relative permeability of unity, and sigma is equal to 0. I don't even have to give that sigma equal to 0 because I've said lossless. And when I ask questions in an exam situation or the like, I'll say it's either lossless. If I say it's a lossless medium, then that one just tells you that its sigma is going to be equal to 0. If I said it was lossy, the sigma is not going to be equal to 0. Or I could say that sigma is equal to 0 or sigma is equal to a given value. It's up to you to interpret what that means. And this is what usually confuses or puts a lot of difficulties to people. So assuming a sinusoidal EX, that is a harmonic time dependence, and it has a frequency of 100 megahertz and an amplitude of 10 raised to minus 4 volts per meter, or 0.1 millivolts per meter at t equal to 0, and z is equal to 1/8 of a meter. You are asked to write down the instantaneous expression for E at any time t and position z. Write the instantaneous expression for h, and 2 will determine the locations where Ex is a positive maximum when t is equal to 10 nanoseconds. So the first thing we do is that we just collect what we have. We obtain the value of the wave number as omega equals to root mu by epsilon, and we see that that is going to be given by the c here is usually the 1 over root mu naught epsilon naught. That is the speed of light in vacuum. Now, since we are dealing with a different medium, we must multiply that by, or we must divide C by the square root of the product of the relative permeability and relative permittivity. And we see that that is just simply dividing C by a half, C by 2, because, or multiplying through by 2. And we get that K is equal to 4 pi by 3. I would advise whenever we are solving problems to leave these values as they look, because many times you'll find another pi somewhere and may cancel, rather than using your calculator all the time to give the decimal points and the like. So whenever you possible, always leave the pi in it, or even the square root, leave it in the expressions. It's usually much easier, unless the square root is a rational number. So we are going to let cos omega t to be the reference time function. This is the same as requiring us to use the real part of the expression of that phasor multiplied by the exponent of j omega t. That's what this one means. And therefore, E of z and t is going to be given by the E of x, and we see that that is going to be given by the value of twice pi f of t, that is what omega t minus kz plus a value, a phase factor pi there, where that value is equal to 0, and we get that E of x is equal to just simply equal to 0, and we get that Ex is going to be equal to 0.1 millivolts per meter. So, and therefore at t equal to 0 and z equal to 1 by 8, we have the following. Phi is going to be given by equal to kz when t is equal to 0, and therefore we must get 4 pi by 3 multiplied by 1 by 8, and we get pi by 6. in radians. That is phi given in radians. Hence, the E of Z is just going to be given by that value, and we get the solution. And B, we look at the magnetic field intensity is given as the Y cap, that is Z cross E over eta, and we get that is just going to be EX divided by eta, and we know that eta is given by the mu by epsilon. It will be given by mu naught multiplied by mu r over epsilon naught multiplied by epsilon r, but since mu r is equal to 1, then it's like the same as the intrinsic impedance of the free space divided by the relative permittivity of the medium square root. And since this is equal to 4, we just be dividing the 120 pi ohms by 2, and we get 60 pi ohms. And therefore, H of Z is just going to be given by that value there. The propagation factor is the same. And therefore, at t equals to 10 nanoseconds, we can equate the argument of the cosine to either plus or minus 2n pi for E of x, a maximum. That is, for it to be a maximum being a cosine, it has to be a multiple of twice pi, okay? An integer multiple of twice pi, so that we are always having unity for cosine. And therefore, we have the following, that 2 pi f of t, 1 multiplied by that value, is going to be given by plus or minus 2 pi, or Zm, the position of the maximum, is just going to be given by that value. And we see it's a whole series of values. It's not just simply one value, 13 over 8. It's what, if you add another 3 by 2n, it will give us the value of Zm again. It will be a maximum there. And we note that lambda is equal to twice pi by k, and we see it's just 3 by 2 meters. And Zm is therefore going to be given by 13 over 8 of n pi, so to speak, meters, n lambda, so to speak. So from there, we shall be looking at Doppler effect next. And this Doppler effect, what I can give you so that you can be thinking about it, is what we have a similar effect in sound. So when you are standing by the highway, just listen to the cars moving. Don't just on an isolated place. The best one is to use a siren, an ambulance. Listen to the ambulance as it is coming towards you from far away, and then just as it moves away from you after passing you. What you'll hear is that as it's approaching you, you'll be hearing as if the sound is increasing in frequency or in pitch. And then as it's going away, you hear like the frequency is dropping or the pitch is coming lower. That is, it's more like saying as it's approaching you, it's going towards the soprano. And when it's going past you, it goes down towards the bass or tenor and the like. Okay? So that is the issue of Doppler effect. It's where there is relative motion between a receiver and a transmitter, something which is generating the wave and something that is measuring the wave. There is an apparent change in frequency. It's not a real frequency in the source, but it's an apparent frequency that is measured. This Doppler effect is also used in telling. That's why the astrophysicists tell us that the universe is expanding, because some stars have been seen to be generating or to be emitting light that is shifting towards the red, and it's called the red shift. And therefore, if it's moving towards the red, it means that the star is moving away from us. How they prove that is actually the universe that is expanding is they are assuming that the Earth is at the center of the universe, and therefore the only way the star may be moving away, it may be moving away from you radially, so to speak. We could be all on the surface of the sphere, therefore the star is just moving away from us on the sphere, and there's no expansion of the universe. But that one, we leave to the astrophysicists. So, with that, unless we have any questions, I'll call this the end of today's lecture. We can continue from there next week. So any question before we leave? Well, since you are not asking any questions, then I'll stop here. Wish you a nice weekend. Let's meet next Wednesday.
Thank you.
Okay, thank you too.